My name is Rian Abdul Waheed and my group partner name is Singh Ahmed. And we are doing this project under the supervision of Dr. Ahmed Ali Shah and co-supervision of Dr. Abdul Aziz. So our project is WG headset-based smart devices controlled through IoT for paralyzed patients. So this is our table of content. In this, we are going to talk about the introduction, the literature review, motivation, problem statement, aims and objectives, methodology, ML models, training and testing, IoT architecture, results, conclusion, future recommendation, and references. So our introduction, brain-computer interface. What is brain-computer interface? Brain-computer interface, BCI, is a technology that allows direct communication between the human brain and a computer, using brain signals like electroencephalography, or betterly known as WG signals. It has the potential to revolutionize the technology of interaction. Like we have the technology of touch with the technology of mouses and keyboards as input devices, but we can revolutionize it and use this command, our brain commands or neural commands, as inputs for these things like a mobile or a computer or anything else. Okay, despite these challenges, the potential benefits of BCI technology are significant, with applications in medicine, gaming, and human-computer interaction. So we have numerous applications of the brain-computer interface, mainly in the field of medicine, gaming, and human-computer interface. So types and applications of BCI. Basically, BCI are of two types. The first type is non-invasive type. A non-invasive type is a type in which a reading is collected from the scalp of the subject. Electrodes are placed on the scalps of the subject on the frontal and prefrontal lobes. And in the invasive, a surgery is required to place the electrodes inside of a human brain. The invasive is more accurate and more reliable in sense of data, but it is more dangerous. It can cause internal bleedings, infections, and in some cases, it can even cause death. So we are using non-invasive type, which also only uses the scalp. I know the signal from it is weak as compared to the invasive, but it is much more safe and much more reliable in the long term. So applications of BCI, medical. In the field of medical, if a person gets injured or hurts his spine and cannot walk any further, we can develop a wheelchair which is controlled by neural commands. And with the help of this wheelchair, the person can have mobility to go somewhere, to do something, to be helpful, and be independent in basic terms. Military operations. This can be used, the brain-computer interface can be used in military operations in unmanned aerial and ground vehicles to control these vehicles. And in this case, we would not have any casualties in case of an accident or any mishap. Gaming. The gaming industries can revolutionize with this technology. So we can use the human brain to control our characters in a game. It would be much more fun and much more realistic. The human-computer interface. The human-computer interface is the combination of all these. Literature review. We did quite a bit literature review, but the main findings were from these papers that are being shown. First of all, a hybrid classifier combination for home automation using WG signals. In this paper, they have discussed WG signals can be used for home automation with AI and open BCI technology. They used a hybrid model for long short-term memory and a classifier for WG signals. And in this, they verified that when they combine two types of classifiers, so it is better than one because it gives more accurate data and its accuracy is much more. Furthermore, drone control based on mental commands and facial expressions. In this, they have discussed the use of mental commands and facial expressions with respect to machine learning and IoT to control a drone with a emotive headset connected in 5 electrodes. Third, the deep convolutional neural network for the automated detection and diagnosis of seizure using WG signals. In this paper, They have explored a 13-layer deep convolutional neural network algorithm to detect normal, parietal, and seizure classes with an accuracy of 88.67%. In the traditional sense, if we look at these ratios, we cannot detect seizures that much often unless it is more severe and in such a case that it cannot be easily cured. So with this, they have detected 88.6% with 88.6% accuracy that a seizure is going to occur. So in this way, they can come in the way of the seizure and give early treatment so that it could not go so much severe or go so much bad. Last, WG signal-based system to control home appliances. This paper presented a method of feature extraction from an electroencephalogram WG signal in real time based on common spatial pattern and utilized this into control for home appliances. Motivation. Our mission and motivation is a product that empowers a paralyzed individual to control to their smart devices using only their thoughts. By processing WG signals and focusing on mental commands, we are working towards a more efficient way for disabled individuals to interact with the world around them. We believe in a more inclusive and accessible future where technology is used to enhance the lives of all individuals, regardless of their physical ability and disabilities. Problem statement. In our society, we can see nowadays a physically challenged human being is almost ignored in every field of life. They are considered as people who cannot do anything on their own and always require the help of someone to do anything. They consider themselves a burden on their loved ones and society. Being in such a miserable state makes one to quit living or kill himself or discard his living purpose. So a physically challenged person can't even light a bulb, turn on a fan, or any electrical device without the help of a second person. They become so much miserable that they think they should die rather than live with such misery. Aims and objectives. The main objective is to develop a product by which even a paralyzed person will be able to control the smart devices. The secondary object is to process the WG signal so to control the external devices, as it is beneficial and is the most efficient form of smart device control for a paralyzed person. As it flawlessly works together towards helping a disabled person, most of the previous work done through eye blinking or body movement, but our project is solely based on mental commands so that a paralyzed person, even a paralyzed person, can enjoy the freedom and independence of not being dependent on any other. Methodology. The methodology is in front of you. First of all, we ask the subject to sit in a specific room or atmosphere, a controlled atmosphere where there is no noise, nothing like this. We acquire the signal. The signal is pre-processed. So we use temporal filtering, spatial filtering, feature extraction to clean the signal of any unnecessary artifacts or noises that we do not want in our signal, which could hinder the accuracy of our product. Furthermore, the signal is classified. We use 4 commands, 4 classifications, basically. Fan on, fan off, light on. With these are sent on to a Raspberry Pi through the help of a ESP8266, which is used for the purpose of IoT. Basically, we are using 2 ESP8266, one which would be connected to the Raspberry Pi to send the signal to the receiving ESP8266, which would be connected to a breadboard or a circuit to control the overall architecture. Data acquisition. As I was talking earlier, the subject sitting arrangement, the subject training about thinking of a specific scenario, data recording and signal monitoring, data collection in a text file for each scenario. So if I talk further of this, the subject was told to sit in a specific manner and be relaxed. The room was a controlled atmosphere with a white background in front of them. We showed them a specific videos of what we wanted them to think about. So once we showed them the videos and we made sure that they are relaxed and are very calm and there is no noise around us. Then we started recording the data. Data recording, as you can see here, first of all, the data is very rough or very spiky. We do not need such data. And the data later from that is a little bit straighter. It does not have such spikes that it could hinder our accuracy. These files are recorded in text files for each scenario. A subject was shown 4 scenarios each. We had 30 subjects, 15 male, 15 female, at the age of 18 to 25 years old. So on left, you can see the distracted data. It is labeled also so. The distracted data, as you can see, it is when there is noise around you, some people are talking, there is a television running, a radio chattering, a song running. So these all contribute to the noise. Or if there are too many electrical appliances around you and they have frequency and inductance, this can distract you from focusing on the specific scenario, and the distracted signal could look like this. The distracted signal is not required by us. We do not need the distracted signal because we cannot use it. It has too much spikes, it has too much irregularities, so there cannot be formed a specific pattern which a machine learning algorithm could remind and learn from to be of use. On the right is the concentrated data. This is the data which we acquired from our subjects in the control atmosphere of our lab and the specific scenario that we made them think of. So data cleaning. This is our raw data. This is the data that we acquired from our subject. Basically, this is the clean data which we acquired from our subject in each scenario. In this scenario, scenario 1, if we suppose it as scenario 1, we acquired these signals and turned it into a text file. As we can see, these are too much. So we do not need all that data because from the starting, when we tell them to think of the specific scenario and we start recording, there's a slight bump in the data set or in the OpenGUI signals so that we can notice. So we recorded each scenario for 15 seconds and we subtracted the starting 5 seconds and the ending 5 seconds from this data and turned this data into this clean data in our Excel sheet so that we would get proper and accurate results each and every time. ML models. We used many models, but the best model with the highest accuracy was the CNN. So, but our data was not so much for the CNN model. As we know, CNN is known as a data hungry model. So we added 3 new columns in the time domain features, which are known as standard deviation, average, and mean. ML models. So conversion of time series to frequency series. The conversion was done basically to get frequency bands. We made our threshold frequency from 2 Hz to 65 Hz. We used 2 filters to get better results. The filters we used were butterpass filters, which only passes the threshold frequency that we set, which is from 2 Hz to 65 Hz, and notch filter, or known as Butterworth filter, which discards at the frequency of 50 Hz. This frequency of 50 Hz is discarded because in Pakistan, all our surrounding equipments, the poles, the electric appliances, all run on 50 Hz frequency. So this could generate a high number of disturbance or artifacts that we do not want in our signal. So model training. We use the EEG model, and the data we had, we specifically designed it to for 70% was allocated to training, 20% was allocated to testing, and 10% was allocated for validations. We also used KFold validations for 10 iterations. As you can see, these are the graphs. On the left, the graph which is rising is the training and validation accuracy. And on the graph on the right is the training and validation loss. We can see on the graph of the left, on the left side, that on starting, it is very low because our model is training and making mistakes over and over, and it is learning from its mistakes, and eventually the accuracy is rising. And on the right, we can see that at the start, the loss is very much high because the model is not trained enough, so it is losing too much data and is not as much accurate. So over time, the loss decreases to such an extent that it is almost less than 10 to 8%. So model testing. The performance of our BCI model was evaluated by analyzing the model performance. The model is tested on the WG dataset and its performance is measured in terms of accuracy. The model gave us accuracy of 89.5%. So this is in front of you is the confusion matrix of our project, of our product. So we gave the command of light on for 16 times. For 14 times, it predicted the correct signal of light on. For one time, it showed us light off, and for once, it showed us fan off, and for 0 times, it showed us fan off. So this is our confusion matrix, and we can see from in here that we have a pretty much high accuracy. The accuracy is 89.5%. So our IoT architecture. Basically, we were using the Raspberry Pi type 4, Raspberry Pi 4 type B, and ESP8266. The Raspberry Pi was set up by installing our SBN OS into it and configuring the basic settings of it, like date and time and all other things of this, and connecting it to Wi-Fi, of course. We used a micro HDMI port to connect it to a display. UC type power supply, and it has USB 2 ports, USB 3 ports, a gigabit internet port, and it comes from various RAMs, from 1 GB RAM, 2 GB RAM, 4 GB RAM, and 8 GB RAM. It is a microprocessor which is so much powerful that it can do too much. On the right is the ESP8266. This is a node which is used for communicating. Basically for IoT, we use it for IoT purposes. Basically what we did was that once our signals was processed from our headset to this Raspberry Pi, then the signal which we wanted, the classified signal was sent from one ESP8266, which was regarded as the sending ESP8266, to the receiving ESP8266, which was connected to the board, or you can say the circuitry which controlled our appliances. So this is it. These are the results. On the left is the light on snippet on Raspberry Pi, and on the right is the light off snippet on the Raspberry Pi. We ran our model, or we executed our model on this Raspberry Pi. As you can see, these numbers which are labeled as 2-2-1141, these all are the connections, show the connection of electrodes and their values at certain different times. On the left at the bottom, you can see there is light on, which was the command which was predicted. And on the right, you can see the command fan off, just before thinking one. So these are the predictions which it mean, and as per the title of these descriptions, it is correct. Conclusion. In conclusion, our project demonstrated the potential of using WG signals for controlling smart devices in IoT for paralyzed patients. By processing WG signals, we developed reliable machine learning models for accurate neural command prediction, enhancing independence and control. Our work is a promising first step towards more sophisticated assistive technologies for individuals with disabilities. Let's inspire more research and development in this area to create a more accessible future. So our future recommendations or future suggestions, or many would call it future works. So these are our future works. In these areas, we will try to improve ourselves. Enhance system accuracy by advanced machine learning algorithms, additional data types, or optimizing electrode placements. Explore adding support for controlling additional devices and functionalities. Evaluate the system's effectiveness, reliability, and user experience over with long-term testing and user feedback. Integrate with other assistive technologies such as prosthetic limb or a comprehensive set of tools. We tried to integrate our project with a prosthetic limb. It was pretty much a successful try. and we are continuously working towards making it much and much better. These are the references. We did not add all the references, but these are some of the references. Finally, thank you.